So, what we learned about inverse functions is we're switching our input and output values for our functions. So we're going to keep that in mind as we look at the graphs, because what that'll translate to is switching our x and y values. So, with this example here, we're going to look at the function 3x plus 2, and we're going to go ahead and say that that is 1 to 1. In fact, let's go ahead and graph 3x plus 2. So this is the line going through the y-intercept at positive 2, and it has a slope of 3. So here's my line. Oh, those dots were a little bit off. Slope of 3, there, and there. Okay, straight line through those values. And then we'll have arrows because it's going to continue on forever. So, in our definition for 1 to 1 is the idea that we have these unique y values. So the idea is that if we look for each of these x coordinates that we have for our function, the y coordinates that are coming through are all different from each other. So what this can translate to is something that we're going to talk about down here, which is the horizontal line test. The idea being that if I draw every possible horizontal line here, then what I'll have is I'll only cross the graph once. And that's exactly what I want. If I only cross the graph at most one time, then that means my function is 1 to 1. If my graph curved down, and say I came down like this, then what I would have are coordinates that have the same y values, and that no longer makes it 1 to 1. And if I draw a horizontal line, that would show that I cross it more than once, and it would fail. So, with that, a linear function is perfect for 1 to 1, which means we can take the inverse of it. So, let's go ahead and find the inverse. So, if I have my function y equals 3x plus 2, then what I'm going to do is switch the y and x values. So I'll switch it to x equals 3y plus 2, and now I'm going to solve for y. So I'll subtract 2 from both sides, divide by 3, so y is x minus 2 over 3. So that's our inverse function. The inverse of f of x is x minus 2 over 3, or if I'm going to graph it, it might be helpful to split up my fraction to think of this as 1/3 times x minus 2/3, so I can see my slope and intercept. So, we graphed f of x there. In fact, I'll label it. And let's go ahead and graph our inverse function. So intercept at negative 2/3 and then a slope of positive 1/3. So what I'll have here is intercept of negative 2/3. I'm just going to estimate this best I can. And then we'll go up 1, right 3. So we'll have a second point there. I'll just do 1 backwards, so down 1. Oops, don't want to do that with my pen. Let's see. Down 1, and then left 3 for a second point right there. And then we'll just connect those. So, here is my graph of the inverse function. So, what we can see here is the graph of our original function and the inverse function. What we're going to do is we're also going to graph y equals x. So I'm going to make this a green line. And y equals x looks like this. Now, why we want to see that line is because there's a property with inverse functions. The property is that when we graph an inverse function, it's reflecting over y equals x. So where we can see that is, well, what's helpful is this intersection right here. Since that's landing on y equals x, it just reflects onto itself. But let's also look at, let's see here, 0, 2. What I can do is imagine this diagonal reflection. So it's like I go diagonally to my line y equals x, and then if I reflect diagonally, there's the coordinate for my inverse function. Similarly, let's see if we can find another good point. Similarly here, except I'm going to start with my f of x function. We have diagonal 1, diagonal 1. And then we can even see here there's like a little jump and a little jump, but it's symmetric. So it's reflecting over this y equals x to get the inverse function. Now that can be pretty difficult to visualize, and just takes practice, and we'll just keep looking at that. Another way this comes through is that by reflecting over y equals x, it's like we're switching our x and y values, and we can visualize this in a table as well. So let's say I made a table for x and my original function f of x, which is the 3x plus 2. And let's just grab some x values. So -2, -1, 0, 1, 2. So if I just plug those in, or if I look at my graph here, like I can see at -2, we're at -4. When we're at -1, we're at -1. And at 0, we're at 2. At 1, we're at 5. And 2, let's see, 3 times 2 is 6, plus 2 is 8. So, with that, I have a table for x and f of x. If you have a table of values, so if you have your coordinates for your graph, it is very nice to create a table for your inverse function. What I'm going to do is create a table for my inverse function. And let's say I didn't have the visual of my graph over there. If you have the table for f of x, so like we were saying, the purpose of this inverse function is to switch your input and output. Well, for my original function, x is my input, f of x is my output. Well, if I'm working with my inverse function, I just want to switch those two sides of the table. So what I'm going to do is where I have my values for f of x, those are going to go under x. So -4, -1, 2, 5, 8. And then for my inverse function outputs, I'm grabbing the inputs from the first table. So -2, -1, 0, 1, 2. So when you're working with graphs, if you have coordinates, if you have x and y values, to make the inverse graph, you just switch them. You just switch x and y, and that's it. And I find that to be a lot easier to do than to visualize this reflection over y equals x, even though that reflection is important, it's good to understand. And that's exactly what we're doing here. We're reflecting over y equals x by switching the x and y values. But computation-wise, there's not even computation here. This is just a little easier to make. So if we look at our table here, we have -4, -2, -1, -1, 2, 0, 5, 1. So we can see those points that we graphed here just by finding our equation on this left-hand side, but we could have also found it with the table of values. So, a few different ways to approach the graph. Either algebraically, by switching x and y and solving, and then just graphing that line. You can visualize it as this reflection across y equals x, or make a table of values for your original function, and then just switch the sides to get your inverse function. Alright, let's go ahead, and our last step here is to verify that this works. So we're going to go ahead and verify by looking at the composite functions. So f of our inverse function, so our inverse function was that x minus 2 over 3. And f tells us to take 3 times the input plus 2. And what we'll have are those 3's cancel out, so we'll have x minus 2 plus 2. Then we'll just have an x, which is exactly what we want. Then I'm going to look at the inverse function of my original function, the 3x plus 2. And my inverse function says to take the input minus 2 all over 3. And we could also plug into this form, the slope-intercept form we found here. Either one, they're exactly the same. So my input's going to be 3x plus 2. In the numerator, that positive 2 and negative 2 will make a 0. So really I have 3x over 3. The 3's will cancel, so we just get x. So that verifies. Plugging the inverse into the original function, that should simplify to x. And plugging the original function into the inverse function should also get x. Alright, so the horizontal line test is a way to determine that the function's one-to-one. So what we're going to do is think about every possible horizontal line, and we should only be crossing once. Then what we have is we'll reflect over y equals x to get the inverse function. Let's talk about in this next example how vertical line test comes through. So what we're going to do is look at our parabola in two forms here. One form will just be x squared plus 2. The other form will be x squared plus 2, but with a restriction on the domain. So let's just look at x squared plus 2. So that's our parabola that's been shifted up 2 units. So if I graph that, I have vertex at 0, 2, and then just my standard parabola shape without any stretches or anything. So here's my parabola. So something we can notice here is we're going to fail the horizontal line test, which is going to tell me that the function is not one-to-one, which means it's not invertible. So those are some pieces I'm getting here. But let's say we didn't know about the horizontal line test. Let's say we just went to invert it anyway. We're switching our x and y coordinates. So the fact that I have 0, 2 means that I would have the coordinate 2, 0. If I have 1, 3, then I would have the point 3, 1. If I have negative 1, 3, then I have 3, negative 1. And so on and so forth. Oops, one more. There. So if I reflect over y equals x here, or if I switch my x and y coordinates, we would end up with this graph. However, is that a function? No. It fails the vertical line test. What happens is when we take the inverse, it's not a function because it fails that vertical line test. And how that comes through is in the original function failing the horizontal line test. So it all comes down to that vertical line test. It just switches direction because the inverse has this reflection. So some things that come through here, if we reflect over y equals x, it is not a function. And that's because it fails the vertical line test. And that's for the red function, or sorry, not function, the red line that we're looking at. So what we see is if y equals f of x fails the horizontal line test, the reflection over y equals x fails the vertical line test. So it's a way of checking before the reflection, just looking at that horizontal line test. As soon as we check that, we can say it's not invertible, we can't do anything with it. So with this one, this is not invertible. So now let's look at this x squared plus 2, so the same parabola, but only for x is more than or equal to 0. So what this will look like is we'll have our vertex at 2, and then we'll have our parabola for everything more than or equal to 0. So now what we can see is we pass the horizontal line test. Every horizontal line we're only crossing once. It's because of that domain restriction we're missing that other half. So now we pass the horizontal line test. So now let's look at that reflection over y equals x. So if I have the point 0, 2, I'm going to have the point 2, 0. If I have 1, 3, then I have 3, 1. If I have 2, 6, then I'm going to have 6, 2. So now, if I look at this reflection over y equals x, if I switch those coordinates around, now I have something that passes the horizontal line test, which means it's a function. So that makes it invertible, is because once we take the inverse, it is a function that we can work with. So this one is invertible. So that's the idea of the horizontal line test, is if we draw the original function and fail it, then we can't take the inverse. Because when we go and reflect it over y equals x, we end up with something that's not a function. However, sometimes what we can do is restrict the domain in a way so that we have a piece of the function that does pass the horizontal line test, and then we can look at the inverse function. All right, last piece here is making a sketch of our inverse function. Again, a few different ways to think about this. You can think about that reflection, or what we could do is think about how some coordinates switch. So what I'm going to do is grab some key points here. So I have the point negative 3, 4. I have the point negative 2, 2. I have the point 0, 1. And 2, 0. And 3, negative 2. So if I want to sketch my inverse function, all I need to do is switch the x and y values. So where I had negative 3, 4, I'm going to have 4, negative 3. Where I had negative 2, 2, now I'll have 2, negative 2. All I'm doing is switching input and output values. So with that, I get some key coordinates for making my graph. So 4, negative 3 is down here. 2, negative 2 is here, 1, 0, 0, 2, and negative 2, 3. And with that, I'll just connect the dots. And there's our inverted function. And we could visualize this as the reflection across y equals x, but just switching the x and y values can be a bit simpler.